Good morning, students. In this video tutorial, I'm going to show you how to run regression in SPSS using a scale-dependent variable and scale-independent variable. Our significance test will be the interval, the b-value, and our strength test will be r squared and r. This should look pretty familiar by now. Here is a student survey from the summer of 2012, and I have my variable view, and all of my scale variables are indicated with a ruler. And I chose these when I inputted the data from student surveys that were given at the beginning of class. So let's pick a few scale variables. We could do the effect of one's opinions on taxes on one's opinion on the economy. These questions were provided using a 1 to 10 scale on the student survey and just rating one's opinion from 1 to 10 on the state of the economy and taxes. You're going to go to Analyze, Regression, and Curve Estimation. Your independent variable goes in the independent box, your dependent variable goes into the dependent box. Make sure that you select constant for the equation, plot models, linear, and you can also click on Display ANOVA table. The ANOVA table will help us explain the sources of variation in the data. This is more useful for multiple regression, but just make a habit out of selecting it from now on, and click OK. SPSS will run its thing, and here is a scatter plot of all of the data points in our data, in the population, in the distribution, if you will. Taxes, our independent variable, is on the horizontal or x-axis. The economy is on the vertical or y-axis. And these are different pairs for each individual student. We have a student here, for example, that provided a 1 for taxes and a 1 for economy. Over here, a student provided 10 for taxes and marked around 9 for economy. Here is our line of best fit, or the least squares line. What this line of best fit tries to do is it attempts to minimize the amount of positive and negative errors in the model. This line represents y predicted, or yp, and that's just SPSS trying to create a model that best fits the points as provided in the scatter plot. It doesn't actually have to go through any particular points in the data, because what it's trying to do is minimize positive and negative errors. When a point is below this line, it is called a negative error, and when a point is above this line, it is called a positive error. What this line attempts to do is minimize the total amount of errors attributed to points falling below or above this line. So here we have our coefficients, and here is taxes, our independent variable. In the next video, I will show you multiple regression in which multiple independent variables will show up, but for now we only have one, and taxes is the independent variable, and the economy, one's opinion of the economy, is the dependent variable. The b is our b-value, which is the relative slope of the line. And the constant shown here is the y-intercept. You can see it corresponds 2.24 and 2.24 over here. What this tells us is that for every single unit increase in x, y increases 0.618. Otherwise, to put this into sentence form, for every 1 unit increase on one's opinion of taxes, there is a corresponding 0.618 unit increase on one's opinion of the economy according to this scale, according to this table, according to the graph, and the y-predicted model. Significance can be shown here, looking at the significance number under coefficients. And what this shows us is that indeed the relationship, because it's less than 0.05, is a significant one. There's a significant relationship between one's opinion of taxes and one's opinion of the economy. If you look at this, that makes sense. There is indeed a positive relationship, a positive slope. If there was no slope, then that would indicate no relationship. Of course, there is another way to check out the significance, but first let's move on to the r squared. Here we have the model summary of r squared and r. What r squared basically means is the same thing as eta squared when we were doing ANOVA. Taken as a percentage, r squared here is 36%, which means, and this is going to be the case with all r squared descriptions, 36% of the variation in the dependent variable can be explained by the independent variable. The perfect r squared, of course, would be 1, meaning 100% of all the variation is explained by the independent variable. R, shown here, is used very similarly to eta in ANOVA testing. So the way you interpret R is, if the R number, which is just the square root of R squared, if the R number is less than 0.25, it is a weak relationship. If it is between 0.25 and 0.50, it is a moderate relationship. And if it is greater than 0.50, it is a strong relationship. So what we have here is a relationship that is significant and is strong, in which 36.6% of the dependent variable, the variation in the dependent variable, can be explained by the independent variable. And written out, this equation for the line here, the y predicted, would be y equals 2.247 plus 0.618x. Additionally, there's another way to check for significance. If we go back here, we can go to Analyze, Regression, select Linear, choose our independent and dependent variable again. It was taxes. And economy. Go into statistics and select confidence interval level 95. Remember, we're using a 95% confidence interval in this course, in which we want to reject the null at least 95% of the time in order to consider a relationship to be significant. Choose descriptives and model fit. Continue. Here we have an upper bound and a lower bound for possible places for B. This is basically saying that we are 95% that B, the coefficient of regression value, or the slope of x, is between 0.330 and 0.907. And indeed, when we did it out, the B value shown for taxes was 0.618, which meant, as I said before, for every 1 unit increase in opinion of taxes, there's an increase of 0.618 on the dependent variable, or the opinion of the economy. Because the B value is positive in this regard for the lower bound and positive for the upper bound, there's no chance, or a 95% certainty, that it will not cross 0. When a slope is 0, that means there is no relationship. So in significance testing, what you want to find is a upper and lower bound that are either both positive or both negative in order to show significance. If they're both positive, then the slope is positive, meaning it's a positive relationship. And if it's negative, the slope is negative, meaning a negative relationship. For increase in x, there's a decrease in y. But if you see a lower bound and an upper bound in which they are different, one negative, one positive, then there's a chance that 0 is the slope, and we are unable to reject the null hypothesis.